So, hello everyone. Today we are starting Module 2 of our course, EE 306. And Module 2 will tell you about discrete stochastic processes. The following Module 3 will tell you about continuous stochastic processes and how they are influenced by going through linear time invariant systems. In our remodeling of this course, we thought it would be very beneficial to give you an initial idea of what a stochastic process is and various notions related to it, like stationarity and ergodicity, through introducing to you discrete stochastic processes, because we believe it's more instructional, it's easier to learn. So, the first thing we are going to discuss is where do we encounter discrete stochastic processes. Consider observing the value of a measured quantity at certain discrete times n equals 1, n equals 2, 3, and so on. Now, for example, suppose I place a temperature sensor in this room and I take a reading every 10 minutes. Okay? And so every 10 minutes, I have one measurement. I can label the measurements as measurement 1, measurement 2, etc. And the reading I take at measurement n will be the temperature at the measurement instant n. So suppose this is 25 degrees Celsius. And I will have this sequence of values, 25, 24, 21, 18, 20, etc., as long as I take these measurements. Okay, this is a very typical situation, given that in our day, our surroundings have a lot of electronic sensors that measure various quantities and report them sometimes through the internet in a paradigm that we call the Internet of Things. So this kind of thing, where measurements are taken, sampled in discrete time and transmitted, is gaining more and more importance today. Let's take another example where an autonomous vehicle sends its location information to other autonomous vehicles or to a central processing location. This is also a very, very current example in our day, where we're talking about fleets of, for example, self-driving trucks or unmanned aerial vehicles, UAVs, and fleets of robots, things like that. In all of these situations, and you don't even need a fleet, you could be talking about a single autonomous vehicle, or a non-autonomous vehicle that you're trying to track. Or think of, you're riding in a taxi cab and you're sharing your location over an application with your friend who wants to know where you are, right? So in those cases, the device, the sampling, the output of the GPS chip, right? And it is reporting this value, perhaps periodically, perhaps according to some other schedule, right, to a faraway location. Okay, so in that example, so suppose this is example 1. In example 2, we're reporting location. Okay, so we could have, for example, the sequence, so x1 could be, in this case, we're talking about location information, like a GPS coordinate, for example. For example, think of Ankara, and I don't remember the exact coordinates of our location, but I could make up something that is not too far off. I don't know, 39 point. Do you remember the rest of the digits? Anyone? I'm just gonna make up some numbers, okay? 8821, comma, 32.4422, okay? That's x1. x2, now you've moved a little bit. So So let's say 32.4500, etc. I'm just totally making up numbers now. So this is another process where we have recorded values and reporting them in time. Now, another more sort of daily life example, you check out the price of gold each day. Okay, every day, you know, you hear on the news the price of gold. Suppose X1 is 963 Turkish liras. X2 is 945 Turkish liras, etc. Okay, so as you get it, I mean, we can extend these examples to infinity. Why do we consider these examples? Because we need to make decisions in our daily life and in our engineering problems. And we want to model these values xn as random variables. But just modeling xn as a single random variable doesn't get us very far into making decisions that involve future phenomena. Okay. So we want to consider the evolution of the sequence of values measured in time. And to make decisions, for example, such as, given the vehicle's location at time t equals 3 seconds, okay, given the vehicle's location 3 seconds ago, so given that my information about the location of the vehicle is 3 seconds old, now I have some uncertainty about the location of the vehicle, right? The location of the vehicle is depending on the velocity. It is, you know, within a certain radius, whose, you know, within in a sort maybe circular region whose radius is determined by how old my previous knowledge of the location is. Okay, so. What are the chances it is dangerously close to another vehicle? No, I need to make this computation in order to make a decision about, you know, whatever the problem I'm trying to solve is. The price of an ounce of gold is $1963 today. So based on this value, what should I do? Should I sell my investment in gold? Now, that's a decision that many people today are faced with every day. Or in terms of health, right? Looking at the recent blood test of a sample of a patient, the doctor decides whether or not to change the dosage of the medication for the patient. This is something that is dealt with, for example, for some patients, the periodicity for making this decision could be once every several months, or could be sooner. So in some of these situations, we're dealing with periodic measurements. The period can be depending on the nature of the application at hand. In the case of blood sugar, it could be larger. In the case of tracking the location of a fast vehicle, it can be order of seconds or milliseconds. And in many applications these days, the measurements may not even be periodic. Okay, we're interested in these days the communication communication research community is trying to design 6G, the sixth generation of communication networks, which deals with semantic communication, which will only sample and send useful information at the right time to the right location to make the best, most accurate decision without unnecessary transmission of data. Okay, so the reason I brought this up, again, it's connected to the Internet of Things and connected to the evolution of communication networks, which basically is my background and my research area. That's why I personally experienced the use of discrete stochastic process models every day in my work. And other people too, people who work in social networking, remote monitoring of anything, machine learning, and health, the stock market, everywhere, a lot of models and decisions are based on stochastic processes. Now, what is a discrete stochastic process? A discrete stochastic process is a sequence of random variables indexed by n, where typically n takes positive integer values. The simplest example is an example that you're already familiar with from your undergraduate probability course, EE 230, right? The Bernoulli process. The Bernoulli process is nothing but a sequence of IID Bernoulli random variables with some parameter p. P is the probability that the given trial results in a success. So we can think of Bernoulli trials, successive Bernoulli trials, each like a coin toss. Each results in a success or failure independently of all others. The probability of success is p. Alternatively, since these are binary outcomes, right, we can think of mapping the results of the coin toss to ones and zeros. So a Bernoulli random variable, as you know, takes the value 1 with probability p. So if you have a Bernoulli p random variable, let's call this xn is distributed as a Bernoulli random variable with parameter p. Xn is 1 or 0. Oops. 1 or 0. 1 with probability p, 0 with probability 1 minus p, right? So a typical sequence that we get is going to be a sequence of ones and zeros. Right. Now, or another possible sequence, for example, is this. Now, every time we make this experiment of independent trials, Bernoulli trials, we get a path of numbers, right? We get a sequence of numbers, ones and zeros. We call that a sample path. So these are different sample paths of the Bernoulli process. The Bernoulli process is this process of generating a Bernoulli random variable at every time. So the Bernoulli process is the process of xn's n greater or equal to 1, and n is integer valued. Now this process is very simple because it's completely memoryless. What does this mean? At any time n, what will happen at time n plus 1 is completely independent of the past as well as the present xn. Okay? In fact, it's also independent of the future. In the Bernoulli process, each of the xn's are independent of all the others. Now, because of this situation, this is not really a sufficient, very useful model for a lot of real life or engineering phenomena. For example, think of the temperature. The temperature in this room shows some dependence in time, right? It's not independently determined at every measurement, right? The measurement I take now is going to be a little bit related to the measurement 10 minutes ago, clearly. So we want a probability model that can capture some sort of memory in the process. Similarly, the price of gold is not determined independently every day, right? If it was the case, investment decisions would be more random. Now, similarly, especially in the case of tracking the location, right? Tracking the location of a vehicle. If the vehicle has finite speed, then the next location is given by the current location plus some value depending on the velocity, right? Some increment that depends on the velocity of the vehicle. All right, so how can we capture this memory? Now, the simplest, essentially, way of capturing this memory is the type of process that we call a Markov chain. Okay, so in this module of the course, we will start by learning about Markov chains, which I really hope and believe that you're going to find enjoyable. So, here is an example. Let me see if I'm in the right location. All right. Okay. Now, what is a Markov chain? First of all, let me verbally define it. In the case of a Markov chain, the value of the stochastic process at time n plus 1 depends on the present, the past history xn, xn minus 1, xn minus 2, all the way back to x0, only through the present value xn. In other words, given the present, the future is independent of the past. This is the simple memory structure. So basically, to give an example from a location, if you know the current location of the vehicle, suppose you also know the speed, okay? Suppose you also know the velocity. If you know the current location of the vehicle, it doesn't really matter to you for your prediction of the next location where it came from, okay? As long as you know the present location. That's the idea. Of course, if you didn't know the velocity, you could infer the velocity from the previous values, and that's a different story. That's more complicated. At the moment, we're dealing with the Markov chain structure where the only thing that's relevant to the future from the past is the most recent value. Okay, that's a Markov chain. So, now let's see a few examples. This example is from the textbook that we're using. Very simple example, really. Suppose that in our current location, if it rains today, then it will rain again tomorrow with probability alpha. If it does not rain today, then it will rain tomorrow with probability beta, independently of the weather in the previous days. So the chances of rain tomorrow depend only on whether or not it's raining today. Okay? Let's define a state space for this process. The state space for the Markov chain is the set of states that the system can be in. Now, in this example, what do you think the possible states are? Exactly. The state of today, which is it raining or is it not raining? Okay, so in this case, in this example, the state space is raining, not raining. Okay. Now, the problem tells us the following model. If it is raining, now, tomorrow, it will rain again with probability alpha. And if it is not raining, it will rain tomorrow with probability beta. So we model it, we find it useful to draw a pictorial representation for this problem. So we put a circle for each state and say if it's raining, it is going to rain again with probability alpha. If it is not raining, it will rain tomorrow with probability beta. So we sample the state once per day, right? And if it's raining today, tomorrow it's not raining with probability what? Excuse me? 1 minus alpha, clearly. Oops. And if it is not raining today, still it's not going to be raining tomorrow with probability 1 minus beta. Okay, we represented our Markov chain with this pictorial representation, the two-state Markov chain. Okay, now for simplicity, we can rename the states as, 0 and 1, but I used in the example 1 for raining and 0 for not raining. Now let's express the probability that it is not raining at time n. It is not raining given that at time n minus 1 it was not raining, and at time n minus 2 it was raining or not raining, etc. So by the Markov property and by the description in the problem, clearly this given xn minus 1, the past history is irrelevant to determining the probability whether xn is 0 or 1. So this probability is equal to the probability that xn is 0 given xn minus 1 is 0, and that is given here as 1 minus b. Okay. Similarly, the probability that xn is 0 given xn minus 1 is 1 is 1 minus alpha. There's a typo here. Okay, any questions? So far, it's very simple, right? Now, so how is this process different from a Bernoulli process? It has memory. If this was a Bernoulli process, every time, whether or not it's raining will be determined by a coin toss, right, with probability what? Now, that's a good question. What is the probability that corresponds to this example? What is the probability of rain in general in terms of alpha? Okay, I'll give you a simple example. If alpha is a half, what happens? Alpha is a half and beta is a half. Right, so half the time it's raining, half the time it's not raining. Is there still memory? No. So basically the alpha equals 1/2 case kind of disintegrates, turns into the Bernoulli case, right? But if alpha is large, for example, alpha is large, what does that mean about the process of rain, the situation of the raininess? If alpha is large, once it starts raining, it will continue for a while, right? Typically. So if alpha is, for example, 0.9, what do you expect? Let me erase this. Alpha is 0.9. If alpha is 0.9, once it starts raining, how long do you expect it to rain? How many days do you, in terms of the mean number of rainy days? Yes. So because 9, said 9? Oh, yes, please. Close enough, yes.
I think the probability is 0.9, so 9 days raining and 1 day not raining.
Think of the geometric random variable. So every day it's raining, the probability of getting out of the rainy state is 0.1. So every day it's like a Bernoulli trial, and how many trials does it take until we get out of the state? On average, that value is 1 over 0.1, right, which is 10 days. All right. So if alpha is than 0.9, the situation is much more bursty than a Bernoulli 1/2 process, right? You see long bursts of rainy days followed by how many dry days? That actually depends on beta. For example, if alpha is 0.9 and beta is also 0.9, what will happen? Beta is also 0.9.
10 dry days.
Beta is the probability of leaving the dry state. Think about it. So on average, once the duration of the number of consecutive dry days is what? One over 0.9. 1 over 0.9, right? Like 1.1. Okay, so in this kind of situation, the sample paths are likely to have a lot of ones and fewer zeros, right? 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, etc. I mean, of course, any possible sequence is possible, but some sequences are more probable. Okay? So, sample paths tend to have more ones than zeros. So now, what is the frequency of ones in a very long sequence? That is something that we're going to explore soon, probably in the next lecture or next week. Okay? But you see that this effect of the memory in a Markov chain makes it quite different. And it can capture a richer set of problems than what we can do with a Bernoulli process. All right, so now here's another example that's first sort of has been inspired by a student that I was his academic advisor of this student, but his name was of course different. So Burak is determined to take Calculus 1 until he passes the course. There is no eviction from the undergraduate program, which means that he is offered an unlimited number of chances to take the course. Okay? However, Burak doesn't study at all. He doesn't show up to the class and he doesn't learn the material. And every time that he takes calculus, the probability that he passes is P, irrespective of how many times he's taken the course before. It may seem unrealistic, but it actually happened. So, so now let's see what is the underlying discrete stochastic process model for this course. Do you have for this example? Any suggestions? Do you think it's memoryless? Maybe it looks like it's deceiving. It's deceiving a little bit. Because, okay, first of all, let's define some xn's. You're right in saying that I didn't really define what I mean by the underlying stochastic process. So I'm going to define it now. So let xn be 0 if Burak did not did not pass the course on attempt n, on the nth attempt, and 1 otherwise. Now we're thinking about a sequence of xn's. All right. What is a sample path going to look like? Who said that?
0 until 1, 1.
Uh-huh. And after, but I didn't look, so n continues. It takes all integer values up to infinity. So zeros, after some point, once it hits 1, it continues as 1, right? Or it could simply be all ones, right? He could pass at his first attempt, and the sequence would be all ones. So a sequence would be like a number of zeros followed by ones forever. These are possible sample paths. Possible sample paths for this random process. Now, how is this process different from a Bernoulli process? Why is this not a Bernoulli process? Remember, again, the probability of passing is P. And the event of passing occurs randomly. So how is this different from a Bernoulli process?
We have limited number of failures, but the success goes infinite.
Mm-hmm.
But Bernoulli, indeterminate, but we have determined the number of zeros.
Mm-hmm.
But the difference is that.
Okay. Yes?
To win state xn, it has to pay n minus 1.
Right. So basically there's a notion of remembering the past, right? Once you're at 1, that's your state, and you will never go back to 0. So let's write the probabilities. The probability that xn equals 1 given xn minus 1 is 0 is what? Given xn minus 1 is 0, so probability the next step is 1. Next state is 1, yes? P. Okay, good. The probability that xn is 0 given xn minus 1 is 0 is 1 minus p. Okay, so far it resembles a Bernoulli process. But how about the probability that xn is 1 given xn minus 1 is 1? 1, right. And the probability that xn is 0 given xn minus 1 is 1. 0. Okay, so this is where it differs, right? So this, by definition, is a Markov process. A Bernoulli process, by the way, is a Bernoulli process a Markov process as well? Yes, it totally is, except it's a trivial kind of Markov process where it has no memory. This, though, is not a Bernoulli process. So let's, in fact, draw the visual representation. Let's, oops. So how do we know it is a Markov process, by the way? Because, for example, the probability that xn is I given xn minus 1 is j, xn minus 2 is k, and all the values up to x0, this probability depends only on the most recent past value xn minus 1, right? Because of this, I mean, this is clear from the statement of the situation. So this is a Markov chain because it has the Markov property. Now, what are the two states? Passed the course, did not pass the course yet, or 0 and 1. Now let's put the transition probabilities together on this diagram. From 0, I go to 1 with probability p. Alternatively, from 0, I go back to 0 next time with probability 1 minus p. From 1, I go to 1. Interesting. Once I get to 1, I'm stuck. Once the process gets to 1, it's stuck there. This is called, by the way, an absorbing state. Absorbing state. Because eventually, all sample paths are going to end up in that state. All sample paths are going to end up showing only values 1. So state 0 is a transient state. Eventually, you will leave that state with probability 1, no matter how small p is, as long as p is bigger than 0. When p is small, it may take a long time to leave state 0, but you will leave it eventually with probability 1. All right. Any questions regarding this? Now, let's talk about transition probabilities. All right. Now, in this example, P is the probability of transitioning from 0 to 1. 1 minus P is the probability of transitioning from 0 to 0. Okay? In general, transition probabilities for a time homogeneous Markov state are the probabilities going from each state to each other state. And we can represent this as a matrix. What are the dimensions of the matrix? We have a number of states in the state space. We're talking about, at the moment, finite. Imagine there's a finite state space with k elements. So we're talking about a k by k matrix of transition probability values. So let's define them. So Pij is the probability that xn is j given xn minus 1 is I. This is called the transition probability. From state I to state j. Right, so we can put all the transition probability values in a matrix. And we call it the transition probability matrix. So the transition probability matrix goes like P00, the probability of going from state 0 back to 0. P01, P02, that's the first row. The second row is the set values for the probabilities of transitioning from state 1 to each other state. P10, P11, P12, and so on. So, what can you say about the rows and columns of this matrix? Right. Each row should sum to 1. Why? Because each row gives us the probabilities of going to each other state starting from that particular state. So the row sum is Pij summation over all j in the state space for some particular state I. But starting in state I, we can go back to I, for example, and we'll go back to a number of states. So this is Pii, Pij, Pik, Pil, etc. Now, starting in state I, we have to go somewhere, including state I itself. So the sum of all of these probabilities should be 1. So this should be 1 for all I, right? So that means the row sums should be 1 in this matrix. And all the entries of the matrix are probabilities, so all the entries are between 0 and 1. So this is actually a very special type of matrix that we call a stochastic matrix, and it has a number of interesting properties that are studied in more in-depth courses in probability. We're not going to go into those things, but those of you who are interested can definitely read about it. So in the rain-no rain example above, P, I don't know what M is here. It's a typo. It's a typo. It just means it's a bug that of my LaTeX typing. So basically the matrix P is alpha 1 minus alpha, beta 1 minus beta. Okay. Any questions regarding transition probability matrix? Now that we define the transition probability matrix, things will become more and more interesting because we will be able to do some math with the transition probability matrix. All right, before we take a break, let me introduce you to a fun and very, very useful Markov chain example. And that is called a random walk. So, think about a state space which is a set of all integers. Now, I'm not limiting my state space to a finite set. I'm taking all integers. For example, think of this stretch of values. Now, think of maybe like a little particle walking on this line, such that at each point in time, think of, for example, every second, the particle either takes a step to the right or takes a step to the left. It takes a step to the right with probability P, takes a step to the left, sorry, not P, in the problem it's A, so let's use the same thing. It takes a step to the right with probability A step to the left with probability 1 minus A. And we are interested in the evolution of the location of this particle. And this can model an infinitely many set of different phenomena in engineering and other fields. I mean, think of games of chance or stock market and many things. And in communications, we use these kinds of Markov chains in modeling queues, where data packets get queued in certain network locations and elements and transmitters and routers and switches and such. Okay, so now, what kind of a Markov chain is this? The state space is all integers. What are the transition probabilities? Pij. the probability of going from state I to state J is what? For every state from I we can only get to I plus 1 or I minus 1, right? So Pij is A if J is I plus 1. It's 1 minus A if J is I minus 1. It's 0 otherwise. So we have a transition probability matrix P that is very sparse, basically has mostly zeros. 0 and then A 0 1 minus A. So maybe I didn't draw this very well. We have zeros on the diagonal, right? We have zeros on the diagonal, and we have well, it is hard to draw because we have an infinite number of dimensions. So I will skip drawing this. But you understand. We have zeros on the diagonal, and we have only A and non-zero elements, right? The very off-diagonal elements, and then the rest are zeros. So, what are some interesting questions regarding this Markov chain, this random walk? Now, we can think of, for example, putting some barriers into this. For example, given that I start at 0, what are the chances that I cross 2 before I hit negative 2? Right? That's an interesting question. And that may remind you of, for example, investments in the stock market. So you start with a certain amount of capital, and your investment strategy is you keep, either every day you win or lose. Your strategy is to quit when you hit a positive barrier or a negative barrier, for example. So what are the chances that you quit by with earnings rather than with a loss? Okay. Another question that is based on this is the cliffhanger problem, where, for example, at some value, for example, at 6, we have a cliff, sort of, such that when the particle hits this location, the game is over. So it's like sort of falling off a cliff. And the question is, depending on the value of A, what is the probability of eventually falling off the cliff? Okay, and you can think about this. It's actually a fun thing to, I'm not going to give you the answer, but you can think about this. Another random walk example on a finite state space is the following problem that I will also ask you to think about. Let me draw it here. And this is the last thing we do before the break for this hour. So there is an insect on the windowsill. Okay, and the windowsill has a certain duration, what do you call, length, okay? And suppose we divide the windowsill into 5 pieces. And at the location number 1, there's a spider web. Okay. And the insect starts somewhere on the windowsill, and it is walking randomly to the right or to the left. If it hits location 1, it is going to be captured by the spider web. If it hits location 5, it is going to be free. Okay? So what are the possibilities for the future of the insect. Okay, how can we model this as a Markov chain? Again, it walks to the right with probability A. It walks to the left with probability 1 minus A. So how can we model this as a Markov chain? What is the state space? There are different ways to model the state space. You can say it's still going around, it is free, and it has been captured, or a more detailed state space that will be useful for us to use the probabilities A minus A. It could be just directly the location of the current location of the insect, right? The current location of the insect takes 5 possible values. So let's put these values down like this. 5 different values. If it is in position 2, next it will be where? Either 1 with probability 1 minus A or 3 with probability A. If it is in location 3, what's going to happen? Either 2 or 4. Maybe I should put 4 here with probability A. If it is in 4, it will end up in 5 with probability 1 minus A. No, with probability A. Or go back to 3 with probability 1 minus A. If it is in 5, it's free. Maybe we can call 5 as the state of being free. If it is 1, if it hits 1, it will be captured. Okay, and it will stay there with probability 1. So that is our Markov chain. What do you think will eventually happen to the fly? What do you think the sample path looks like? Exactly. So there are 2 possible future fates for this fly, right? Either for this, insect. Either it's going to get captured, and that's the end, or it will get free, or that's the end. So there are 2 possible types of sample paths. So a sample path would go like 2, 3, 2, 3, 4, 3, 4, 3, 5, 5, 5, 5, 5, or 2, 3, 2, 3, 4, 3, 2, 3, etc., and then 2, 1, 1, 1, 1, 1, 1. Okay, all possible sample paths fall either in this category or in that category. Oh, that's interesting. So we will be able to analyze. So this is the case with 2 different absorbing states. We will be able to analyze the probabilities of these eventual outcomes. And we'll do that in the next lecture and the one after.